Okay, problem number 19. Let's change that there. The turbines in a hydroelectric plant are fed by water falling from a 50-meter height. Assuming 91% efficiency for conversion of potential to electrical energy and 8% loss of the resulting power in transmission, what is the mass flow rate of water required to power a 200-watt light bulb? Okay, so we got a... let's see. This is a potential energy question. The potential energy lost of a unit of water falling from a 50 unit mass of water. The potential energy lost of a mass m of water falling from a height z, falling from an elevation dz. The potential energy change of a mass of water experiencing an elevation change delta z may be let's see. It seems kind of pretentious to word it like that. Let's try it in plain language, then we'll go from there. The potential energy of water is converted into electrical energy. The first step will be to calculate the total amount of available potential energy to be converted. Then the efficiency figures will be applied to calculate the amount of energy that the hydroelectric plant equipment is able to extract from the potential energy, from the available potential energy. As the water falls from its 50 meter high state to a 0 meter low state, low energy state. Extract from the no, that's fine. The available potential energy. The potential energy of mass m of water experiencing elevation change delta z is equal to, and we'll put an equation, delta U is equal to mg, then we'll go delta z. That's a potential change in mass. Okay, and then the amount of energy, the amount of so we don't know the amount of mass. So we want a mass flow rate, don't we? So this question brings into the question of rates, doesn't it? Mass flow rate, yeah. So let's go ahead and do that. Mass, if I recall correctly, the way to show this is to do a superscript, maybe? Alt A. Alt A dot? No, that's not the right way to do that. How do I do that? I need to put a dot above that thing. Nope. 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 Yes. Come on. What's the shortcut? Ugh, does it tell me? What's the shortcut for that? Insert an accent. Insert accent above. Ah. A dot. Alt dot. Oh, really? Okay. Let's try that again. M alt dot A. So let's do a where explanation. Where, and we'll M, which is alt dot, is the mass flow rate. Mass flow rate, and then we'll say that is in units of kilograms per second. And G is the gravitational acceleration, and we'll also put in a thing for the delta U, not delta Y, delta U. All right, delta U is, what are you? You're the potential energy change in potential energy, and your units are well, it has to be a rate. So we'll do that. Alt do. Change in potential energy flow rate, or potential energy conversion rate. No, not quite. Potential energy. Let's just take the question of rates out of it, just for now. We're almost there, but I need to make one more explanation in a paragraph or something. Yeah, they don't really talk about rates yet, do they? However, in order to calculate a rate, change potential energy over time. I could say the amount of potential energy available per unit time from a mass flow rate let's just do that. M dot of water experiencing elevation change is equal to, let's just do that. Saves me some work. That is joules per second, or watts. Joules per second, or watts. This is definitely kilograms per second. And then we got the dz, which is the elevation change. And we won't worry about signs at the moment. Well, maybe we could. Well, we're not given notation yet, so we could do something like this. Just be explicit and say z initial minus, nope, z final minus z initial. Will that do it? Z final is going to be lower than z initial, so this will be a negative. So this will be work done on the environment, maybe? I'm used to doing final minus initial in things, so. The amount. So negative usually means energy is flowing out. So the amount of energy, the amount of potential energy available per unit time available to perform work is that. Okay, and let's just go ahead and do that. Z sub f minus z sub I, elevation change, and yeah, that should work with that. Then let's see. So we're given an amount of work to perform and some efficiency figures. So let's do an equation for work. The amount of work that the hydroelectric plant is able to have the water perform. The amount of work that the water the flow of energy in the form of electricity that the hydroelectric plant is able to extract can be written as an equation like so. The amount of work the water is able to perform on the hydroelectric plant equipment in order to produce electricity Maybe that's not the best way to say it. The amount of recoverable work the water is able to perform with the help of the hydroelectric plant and electrical transmission lines can be written as an equation like so. Yeah, I'm satisfied with that. Let's go ahead and put an equation in. So the work is equal to the flow rate of potential energy that can be converted, but also times the conversion, the efficiency, 91% and 8%. 91% efficiency. Was there a way to write efficiency? I forget. 1 minus 0. What was the transmission loss rate? 8% loss. So if we write this out, okay, so that's the amount of work. The amount of work that must be done, that must be performed. The problem asks for the required mass flow rate needed, mass flow rate of water needed, water M, needed to power a 200-watt light bulb. 200. This is the same as solving for W. The variable W, no, excuse me, same as solving for m dot given W ZF minus ZI equals a fall of 50 meters. And we'll just do a colon and say, all right, here we go. Several equations. Solve for m dot. And we'll take this. M dot equals this big mess over W. Or does it? No, other way around. M dot equals W over this mess. And Yeah, that should work out. So let's go. Let's plug in some values. Watts is 200 watt. Below we have, well, we didn't give a value for it, but let's use a previous value. What was the, are we given gravity? You're not given gravity. Let's just use what we had before. 9.812 or something? 9.813. Yeah, let's just use this. Assumptions. G is equal to that. All right, so we'll use that. Times negative 50 meters times 0.91 times 1 minus 0.08. All right, let's do the same thing as I did before. Put all the numbers together. 200, 9.813 times 50. Let's go ahead and put a negative over here. It's negative because we're doing work on, this is water doing work, so energy is leaving the water. Times 0.91 times 1 quantity, 1 minus 0.08. Just be explicit about these numbers. All right, now comes the fun part. Watts. Meter. Let's see, watts. Definitely meters down there. Second squared. Meter squared. Okay. So let's do a unit conversion. We want to go from watts into something else. We want to go into kilograms. So kilograms. Watt is the same thing as a joule per second. Joule per second, and that is the same thing. Let's see, a joule is the same thing as a kilogram meter per second squared. Wait, meter squared per second squared. Okay. And now that we got kilograms, everything should cancel out. In theory. Alright, let's put this big number in here for now. Let's see. Watts cancel. It's kind of hard to see. Let's go ahead and just put these in more simplified terms. This is joule for sure. This is watt for sure. This is second for sure. This will be kilogram for sure. meter squared for sure. This will be joules for sure. Be second for sure. Okay. Does this work at all? I think it will. Equals that. Alright, so watts cancel. Watts cancel. Second squared up here cancels with this one. Meter squared cancels. Joules cancel. You know what? I'm just going to write them all out. Okay. What? What? Second squared. Meter squared. Meter squared. Joules. Joules. And we get kilograms per second. Great. That's exactly what we want. All right. Handy dandy calculator. What do we got? We have negative 200 divided by 9.813. Let's see. Negative 200 divided by quantity 9.813 times 50 times 0.91 times subquantity 1 minus 0.08, close subquantity, close quantity. That should give us negative 0.486888789 kilograms per second. Let's see here. Yeah, okay. M dot. And I guess we can interpret this as, well, the negative sign came from the fact that we used this convention. But we'll just put that in the explanation. Okay. So the let's see, do you want to get rid of the negative sign somehow? So W is the work done by the water. The negative sign can be interpreted as the flow rate of water going up, I guess. Going from the initial state to the final state. Initial, final. Ah, well. The mass flow rate of water required to the negative sign for M dot is from the convention used in equation. We're in problem number 19. Delta U. Meta shift. Problem 19. Delta U. Delta U dot. work is where potential energy change where the potential energy change is of the water. I guess we could put a negative in here. Yeah, let's just put a negative in here. No, let's just keep it. The negative sign for Is there a way to remove it? Guess is the amount of work done by the hydroelectric plant, which is negative because it's receiving work, or energy is flowing out of it. Well, it's definitely flowing out of the water, for sure. So the hydroelectric plant, if it receives it, it's a negative. Yeah, okay. The mass flow rate of the water required to power a required to perform 200 watt of work. The continuous mass flow rate of water required to perform 200 watts of continuous work powering the light bulb is 0.48. Now, is there any, what's a sig figs in there? I guess efficiency. 0.49. power the 200 watt light bulb is 0.49 kilogram per second. Did they ask for units? I guess that's a mass flow rate, and they asked for mass, so I am happy. Liter-wise, a liter of water is a kilogram, so this is about half a liter per second. So problem 19, answer. Okay, that should be it. Okay, now for